Hello, this series of video lectures explains the ARM processor and its complete instruction set. This very first lecture of this series covers the basic features of the ARM processor and the detailed explanation of its functional block diagram.
ARM is acronym of Advanced RISC Machine. Formerly it was known as Acron RISC Machine. After the name of the company Acron, which developed this processor for the first time. But later on it was renamed as Advanced RISC Machine. You know there are two types of computers, RISC and CISC. Reduced instruction set computer and complex instruction set computer. ARM is RISC type of machine. Machine means microprocessor. Actually ARM is a 32-bit processor. So it is only the CPU section of the computer. But unlike other processors like say microprocessor 8085, 8086 and so on, this ARM is not available as an independent IC. But it is provided in the form of a circuit which can be used by different microcontroller developers. Different companies which develop their own microcontrollers, they use this processor as their CPU so that they can add some additional functional blocks as per their requirement, and those functional blocks like memory section, IO sections, serial control section, etc., to make the microcontroller suitable for the required application. And therefore there are a variety of companies which develop their variety of microcontrollers, but all of them are using same CPU, which is ARM, and therefore it is typically called as an ARM core. All these microcontrollers, they have same core, ARM core, or same CPU section. The advantage is that because the CPU section is same, the instruction set for all these microcontrollers remains the same. That means the basic assembly language for programming of these microcontrollers remains the same, and therefore similar software can be used for all these microcontrollers. The another advantage is that because an independent company is focusing only on the design of this CPU section, it can be developed with all the necessary features, the whole of the processing power, and therefore this CPU is well developed CPU, and that advantage is taken by the other microcontroller developers. So these are the two basic advantages of this kind of methodology, that CPU section is developed by one company while uh, it is used by different microcontroller developers to develop their own microcontrollers for various dedicated applications. For example, you can have a look at the microcontrollers provided by Philips. So these are the some microcontrollers which are the Philips microcontrollers. They are using different ARM cores. For example, if you consider LPC 2138, 2148, 2378, etc., all these microcontrollers, they use ARM7 as ARM core. Similarly, these microcontrollers use ARM9. There are successively higher and higher versions of the ARM core, and they are used by the various updated microcontrollers. So that's the idea of the ARM processor. The processor has typical features. Let's discuss them one by one. One of the feature is its load store architecture. The ARM CPU has a register file inbuilt, and that file is typically made up of about 16 32-bit registers. The ALU section of the ARM can process only the data which is present in this register file, and therefore the the whole data which is to be processed by the CPU should be present in this register file. But actually the major data is normally available in the main data memory or the system data memory, which is outside the CPU section. And therefore whenever the data is to be processed, whenever this data which is present in the system data memory is to be processed, first of all it has to be copied into the register file. It should be loaded into the register file. Then after doing the data processing, whatever the results are obtained, those should be stored back to the system memory. And therefore there are two specific instructions which are available for this microprocessor or this ARM core. Those are load and store type of instructions. Load instruction allows the data to be copied from system memory to the register file, and after processing, the store instruction allows the results or whatever data is obtained finally to be stored back into the system memory. So that is why the ARM is said to have the load store architecture. Next feature is all the instructions of ARM are of fixed length. Every instruction is 32-bit wide, and therefore when the instructions are stored in the memory, every instruction occupies 4 memory locations. For example, single 32-bit instruction will occupy 4 successive memory locations. Second instruction will occupy the next 4 memory locations, and so on. So that's how the program or the set of instructions is organized in the memory. The feature is that every instruction is of fixed length. You know, the main memory of ARM has 32-bit address. That is also shown in this diagram. Every location has 32-bit address. And of course, because the memory is oriented, it is byte oriented. The instructions are to be stored in successive locations with one instruction in 4 successive locations as shown here. The next important feature is that it has 3 address instruction format. For example, the typical instruction, add instruction for this ARM processor can be like this. It is add rd, rs, rn. This instruction will add the contents of registers rs and rn from the register bank, and the result will be stored in the third register called as destination register, again from the register bank. Here what we can see is that the source operands are different from the destination operand. So this is the typical format of what is called as 3 address instruction. In the processors like, say for example 8085 microprocessor, we know this kind of instruction, say add B. It's a 2 address instruction. The operands are stored in, say, accumulator and B, and the result is stored in the same register accumulator by replacing one of the operands. Or maybe add immediate data. The result is again stored in the same register which initially holds one of the operands. But here the result is stored in a separate register. So that is the concept of 3 address instruction format. Because the size of the instruction is quite large, made up of 32 bits, some of the bits are reserved for indicating the operation, say opcode, and then some set of instructions, some number of bits are used to indicate operand 1, then operand 2, and a destination operand. So it is possible that addresses of all these 3 operands along with the opcode can be put in a single instruction, because the instruction is typically wide enough, made up of 32 bits. This is the functional block diagram of ARM core. Actually it is a simplified block diagram that shows all the internal functional blocks within this ARM core. As we have seen before, this shows a register file which contains 16 32-bit registers that holds the operands. This register file is made up of 16 registers R0 to R15. Each register is 32-bit wide. The data from this register file is supplied to the ALU section on the different buses. This is 32-bit ALU. One operand is received on A bus. Other operand is received on B bus. The two operands are processed and the result is stored back into the destination register. The data, 32-bit data supplied on A bus directly reaches the ALU, while the 32-bit data on B bus is supplied to ALU through a circuit called as barrel shifter. The barrel shifter is a circuit that can either shift or rotate a 32-bit number to left or to right by say n bit position. As we know that when a number is shifted left by say n bit position, effectively it is multiplied by a factor 2 raised to n. Similarly, when the number is shifted to right by n bit position, effectively it is divided by 2 raised to n. So the barrel shifter can perform these operations simply by shifting the number either to left or to right. Therefore, this kind of operation can be performed in a single step. For example, an operand A and operand B taken from the register file. B is multiplied by some factor 2 raised to n, here it is 2 raised to 3, say 8, and then the actual addition is performed by the ALU and the result will be stored in C. So this type of operation can be performed in a single step. You can understand, for example, the content of register Rm will be multiplied by some factor 2 raised to n, or it can be divided by the factor 2 raised to n by using the barrel shifter, and then the result can be added to the second register Rn by the ALU section, and the result can be stored in the third register. So this whole operation can be performed in a single step because of availability of this barrel shifter. So that's the purpose of the barrel shifter. The ARM core contains a unit called as multiply and accumulate unit. The multiplication can be performed by ALU section, but it performs the multiplication by the process of repeated addition. Particularly when you are going to multiply two 32-bit numbers, this process can take a quite long time. There are some operations, particularly in the digital processing, you need to perform such multiplications every now and then, and therefore they are to be done quite fast. And therefore in ARM core a separate multiply and accumulate unit is provided, which can perform the multiplication at much faster rate. It is actually a multiply and accumulate unit. It can multiply a 32-bit number from register Rn with another 32-bit number in register Rm and add that product into a third register, and then the result can be stored into a fourth register. So that's how this multiply and accumulate unit works. There is an instruction called as multiply and accumulate of this ARM processor. It is multiply and accumulate RD, Rn, Rm, array. It performs this kind of operation. Rn and Rm are multiplied. The product is added to the third register array, and the whole result is stored into the fourth register RD. So this kind of operation can be performed by a single instruction due to the availability of this block called as multiply and accumulate unit. Now let us consider the address, data and control buses, the system buses. You know, this CPU section is connected to the other functional blocks in the microcontroller through three kinds of buses: address bus, data bus and the control bus. The control bus is not shown here. The address and data buses are 32-bit buses. Address bus carries the 32-bit address of the operand in the memory, or maybe the operand in the IO port. The address register is a 32-bit register which holds that address which is to be sent on the address bus. In case it supplies an address of an instruction, that instruction is fetched and then it has to supply the address of the next instruction. For that there is an incrementer circuit which increments the content of this address register and puts it back into the register, so that next time it will send the address of the next instruction. Okay, that's how this incrementer increments the address in the address register automatically after fetching every instruction. Let's consider the data bus. It's also 32-bit bus. The data bus carries 32-bit instruction or 32-bit data, because the instructions and the data are stored in the same memory. You understand that this, therefore, ARM uses the von Neumann architecture, where the data and address both are stored in the same memory. Both are 32-bit wide. When the data bus carries 32-bit instruction, that instruction is received in the instruction decoder. It is decoded and accordingly the instruction is executed. But when it carries 32-bit data, that data will be either it will be loaded into the 32-bit register in a register file, or a result in a register file will be given out on the same data bus. So data will be either loaded into the register file or it can be stored from the register file to the external memory. There is a sign extend block in the path of this data bus. Particularly when the data, which is 32-bit data, is being read from external memory to the register file, it passes through a sign extend block. Let us see the purpose of this block. This block is typically needed when you are working with signed numbers, and particularly small size signed numbers. You know, ARM is a 32-bit processor. That means it can operate on 32-bit data. The ALU is basically 32-bit wide. But it is also possible that your data may be of smaller size, maybe 16-bit data. 32-bit data is called as a word. 16-bit data, say, maybe half word, or the data may be even smaller, of smaller size, maybe in the form of bytes. Such data is stored in the memory as shown here. For example, a 32-bit data words, they occupy 4 memory locations. So single 32-bit data word is stored in 4 locations, consecutive 4 locations. But when you are working with half words, which are 16-bit wide, then each half word, the data half word will occupy 2 memory locations. Okay, like this. Or even it may be even smaller, it may be a byte in the form of bytes. So then every byte will occupy single memory location. So that's how that data is stored in the memory. But for the purpose of data processing, these data of different types, they are required to be loaded into the register file, and the register file is made up of 32-bit registers. So whenever you want to load a 32-bit data into a 32-bit register, there is no problem. But when you want to load a smaller size data, maybe 16-bit data or a byte data, is to be stored into the 32-bit register, then you have to take some proper care. Particularly if your numbers are unsigned numbers, then there is not much a problem, because if, for example, if you are having a 16-bit unsigned number stored in the memory and you want to copy this number into a 32-bit register of the register file, then simply all the higher 16 bits should be loaded with 0. Okay, then the value of this complete 32-bit number will be same as the value of this 16-bit number. So as far as unsigned numbers is concerned, it is straightforward that by simply filling all the higher bits by 0, the 16-bit number or even smaller size 8-bit number can be converted into a 32-bit equivalent number. But when you are working with signed numbers, then your 16-bit number, for example, if it is a signed number, then the most significant bit represents its sign. Okay, in this case this number is positive because sign bit is 0. Here the number is negative because the sign bit is 1. When such signed number is to be loaded into a 32-bit register, then it is required that the sign bit should be extended to all the higher bit positions in order to keep the value of this 32-bit number same as the original number. So in case of this sign bit 0 is extended up to 32nd bit, whereas in this case this sign bit 1 is extended up to the 32 bit. So in both the cases you can see that here, even here the value of this number is same as value of this number. Both the numbers are negative. Okay, here also the value of this number will be same as this. So here it is required that while loading such small size signed numbers into 32-bit registers, the sign bit is required to be extended for all the higher bit positions. This job is done by the sign extend block. So sign extend block is typically needed when you are working with signed numbers. When you want to store a result back to the memory, is not a big problem, because if the result is 32-bit, it will be stored in the 32-bit register, but it may be having a small value, maybe a 16-bit value or even 8-bit value, and it may be a signed or unsigned number. In any case, the number, when you want to copy that number into the memory, only the lower bits up to the sign bit should be loaded to the memory, and the value will remain unaffected. For example, if you want to, if this is your result, 32-bit result, signed result in the register file, then while putting this back into a 16 as a 16-bit number, the lower 16 bits should be copied to the memory. Okay, that includes the sign bit, and all the higher bits can be ignored. Similarly, if you have this signed result in the 32-bit register in the register file and you want to store it back to the memory as a 16-bit result, then these 16 bits should be simply copied to the memory. All the higher bits can be ignored. The sign bit, which is a part of these 16 bits, will go as a sign bit along with that number. And therefore, while putting the results back to the memory, you don't need any additional adjustment. But while putting a number, particularly small size numbers and signed number, to the 32-bit register, you need a process called as sign extension, and that is actually done by this sign extend block. Now let us discuss the detailed structure of this register file. Here we have seen that the register file apparently contains 16 registers, R0 to R15, 32-bit registers. Actually, if you consider the complete architecture of this register file, it's typically as shown in this diagram. Actually, there are different operating modes of this ARM processor. which are shown here. 1, 2, 3, 4, 5, and 6. You can see that there are 6 operating modes. Actually, there are 7 operating modes, but user 32 and system modes can be considered to be similar as far as the register file assessment is concerned. So we can imagine that there are 6 different addressing modes. In a given addressing mode, these are the registers which are visible to the programmer. So that means here you can see that only these registers will be visible in this mode, only these registers will be visible in this mode, and so on. Let us consider one particular mode, for example user 32 mode or user 32 or system mode. Then in this mode you can see that total 16 plus 1, 17 registers are actually visible to the programmer. Those registers are R0 to R15, 16 registers, and one more register called as CPSR. It is current program status register. We'll discuss about this later. Now out of these 16 registers, you can see that R0 to R12 are used for general purpose storage of data, or to store the operands and to store the result. Whereas these 3 registers R13, R14 and R15 are some special purpose registers. If you see this R15, it is nothing but the program counter. It's a 32-bit program counter for the ARM. So there is no separate register. This register itself works as a program counter. So you can see that in all the operating modes, this register is seen everywhere. Secondly, R13 is the stack pointer. You know, stack pointer is used to point to the last element stored on stack. Usual function of the stack pointer. It's also a 32-bit memory pointer. R13 is stack pointer. R15 is program counter. Now let us see R14. R14 is called as link register, LR. The purpose of this register is that when from a program you call a subroutine, the execution is transferred to the new address. But before that, the content of the program counter is normally pushed on stack. In ARM, it is not needed because this register is provided for that purpose. So when a subroutine is called, the address of the next instruction is stored in this link register, and then the program counter is loaded by the new address so that the execution is transferred to the subroutine. So for example, if you have a main program like this and you are giving a call instruction call to a subroutine, subroutine is here, then when this instruction is fetched and is being decoded and executed by the processor, the program counter will hold the address of the next instruction. So during execution of this instruction, the content of the program counter is saved in this link register R14, and then the program counter is loaded by the new address of the start address of the subroutine. Okay, so that the execution is transferred to the subroutine. So that's how the call instruction operates. When the subroutine is executed, when the processor comes to the last instruction, the return instruction at the end, it simply copies the content of the register R14 back to the program counter, so that the execution is transferred back to the next address after this calling instruction. So this is how R14 is used to store the address of the next instruction when a subroutine is called. This avoids the need of pushing of this address on stack. You know, when an address is required to be, when it is to be pushed on stack, you know, stack is in the main memory of the system and it is outside the CPU. And therefore, while pushing the content of the program counter on stack, the processor has to provide the address on the stack, then it has to generate a control signals, and then this address will be saved in the external memory. That takes considerable amount of time, typically depends upon the speed of the memory. So this is avoided here because of availability of the register R14 or the link register. Simply the content of the program counter is just copied into R14 and the execution is transferred to the subroutine. So this saves considerable amount of time. Of course, when you go to the subroutine and then if you are going to call some another subroutine from a subroutine, which we call as a nested subroutines, then of course you have to take more care. See, for example, this is your main program and here you have called a subroutine. This is the subroutine, and as we have discussed now, the address which is present in the program counter will be loaded into R14 and the execution will be transferred to the subroutine. But in the subroutine, when you call another subroutine, say call subroutine 1, then as usual that content of the program counter will be loaded into R14, but that will erase the initial content of R14, and therefore before giving this instruction the programmer has to take care to push the content of R14 on stack. So before giving this call instruction in a subroutine, the content of R14 should be pushed on stack so that R14 will become vacant, and then you can give this call instruction. During execution of this instruction, as usual, the content of the program counter will be saved in R14 and the execution will be transferred to the subroutine. So this is an additional precaution required while executing or implementing nested subroutines. As at the end of this subroutine, obviously R14 will be copied back to the program counter so that the execution will come back here, and then again when this subroutine ends, now the content of the stack top should be copied into the program counter so that the execution will be go back to the main program. So that's the use of link register. It avoids additional delay as far at least when you are calling for the first time a subroutine. There is one more register which is CPSR, as we mentioned before, current program status register. This is actually a flag register. We'll discuss the details of this later. Now let us see other modes of operation. Actually, the user mode or the system mode is the basic mode in which most of the programs they operate, or the most of the time your processor operates in this mode, and all the remaining modes are invoked under certain situations. We'll discuss them later. But now let us see how the different registers are visible in the different modes. For example, when this mode is invoked, FIQ mode, then you can see that registers R0 to R7 which were available in this mode are still available in this mode, or they are still visible here. But R8 to R14, these registers are now replaced by new set of registers called as R8 FIQ, R9 FIQ up to R14 FIQ. And therefore, when the mode is changed from this to this new set of registers will be available to the processor. Program counter remains the same. Similarly, you can see that an additional register called as SPSR FIQ is now visible. It is saved program status register. Saved program status register. So this is an additional register which becomes apparent in this mode. So that these are the registers which are visible in this mode. Similarly, in every mode there are the registers which are visible are shown here. So you can see that in all the remaining modes, supervisor, abort, IRQ and undefined mode, you can see that the R0 to R12 are available as before, R0 to R12 are available as before. R13 and R14 are simply replaced by new pair of registers in every mode. Okay, and additionally, this is the additional register which is made available, and this is how the different registers are visible in the different modes. So when the processor is operating in a given mode, only certain set of registers is visible, are accessible to the processor. So you can see that in all, if you consider this 16 plus 1, 17 registers in user mode, and additionally these are shaded registers which are shown here. These are called as banked registers. These are totally 20 in number, and therefore 17 plus 20, total 37 32-bit registers are actually implemented in the CPU in the register file structure. But in a given mode of operation, only 17 registers are visible in this mode, 16 plus 1, and in all the remaining modes, in every mode there are 18 registers. This is an additional register. So 16 plus these 2, only 18 registers are available in all the remaining modes. So that's how the register file is implemented, and only certain set of registers is visible to the programmer and accessible by the CPU in the given mode of operation.